Hi, and welcome to the lecture on generalized linear models for binary data. In this lecture, we're going to focus on instances where the outcome is a 0 or 1 random variable, so it can only take two levels. And this occurs very frequently in most analyses. For example, in biostatistics, we're often doing things like survival analysis where people are either alive or dead at the end of the study. For example, a cancer study. We can look at wins versus losses like we're going to do today, or successes or failures of any kind. And our model is going to be, we're going to model the data as if it's a bunch of coin flips where the success probability potentially depends on a collection of covariates. Now, if you have any collection of zeros and ones where the success probability is constant and they're independent, then the total number of successes or failures is a so-called binomial random variable. Okay, so binomial random variables are handled by binary logistic regression in the special case where the covariate is just constant. Okay, so we're going to cover two cases, binary and binomial, by covering the binary case. So as a motivating example, let's look at this data set that Jeff Leake organized when Jeff Leake is another one of the instructors in our data science specialization. He teaches the practical machine learning, getting and cleaning in data, and the data scientist toolbox. So in this case you can get the data here, but it's also in the GitHub repository. The data set here has the Ravens win number coded at ones versus zeros, whether or not the Ravens won coded as a factor variable, wins versus loss, the score, Ravens score, and the opponent's score. Now in this case we're just going to look at to what extent the Ravens score predicts whether or not they won. Okay, so you can imagine if you were in the front office for the Ravens, who I forgot to mention this, the Ravens are a U.S. American football and a National Football League team, and based in Baltimore. So we all love the Ravens around here. So you can imagine if you were in the front office for the Ravens wanting to predict wins with a lot of covariates. Score would be one of them, opponent's score would obviously be one of them, and so on, but you'd want home versus away. And I think you can understand the principles of binary logistic regression just by looking at this example, and I hope extending it, given everything that we've learned about multivariate linear models, will carry over very easily for you. So I just want to remind ourselves, we probably don't want to fit this data with linear regression. If we were to model the probability of a Ravens win, or the event of a Ravens win, 1 versus 0, as a linear regression, we wouldn't be honoring this equation here. Wouldn't actually hold true for sure, right? Because usually we assume the errors are Gaussian. It just would not hold. Now that isn't to say that occasionally fitting binary data with a linear model is the worst thing in the world to do, but it's usually only a quick first thing that you do before you then move on to fit something like a logistic regression model. So here we fit the linear regression in R, and you get the output, and you see what the model is trying to get at. The slope is trying to get at the probability of a Ravens win. However, you can get slope estimates that are negative or above 1 if you fit a linear regression model. Again, it's not the worst thing in the world to do. Sometimes, if you're doing something quick, you have to do it, but probably preferable would be to model the odds. So just to remind ourselves what the odds are, if we have a binary outcome, which in this case is whether or not the Ravens win, we want to model the probability that the Ravens win. So I'm going to get my pen here. The probability that the Ravens win. So we're going to model it like it's a bunch of coin flips. However, the success probability will differ from game to game depending on how many points the Ravens scored. Okay, so that's the probability we want to model. So the odds are defined as the probability over 1 minus the probability, and in a couple of slides I'll describe more about the history of the odds and how people think about it. You can go backwards, by the way, from the odds to the probability, in that the probability is equal to the odds over 1 plus the odds. Okay, so you go forwards from the probability to the odds by taking the probability over 1 minus the probability. You can go backwards from the odds to get the probability by taking the odds over 1 plus the odds. So the two things are exchangeable. The log odds then is just the log of the odds. And we use that so commonly that we gave it a name, and it's called the logit. So the logit is simply the log of the odds. So what we're going to do is put the model on the log of the odds. So I think we've talked a lot about linear versus logistic regression, both in the last lecture and in this lecture, describing what are some of the considerations for why we want to probably do this with logistic regression. But the main thing is that the model assumptions clearly don't hold for linear regression. They're obviously, the inferences probably are not anywhere near correct, or we have no faith in them. But let's just draw the connection between the two so that we can relate what we're doing in logistic regression back to what we did in linear regression. So for linear regression, we built models like this, where the outcome was the intercept plus a slope parameter times the predictor plus an error term, which is a nice way to write out the model and convenient. But another way to write out the same model was just to say that the expected value of the outcome was this linear relationship. So the expected value of the outcome, in this case, the expected value is of a 0-1 random variable. The expected value of a 0-1 random variable is the probability. So the expected value of a fair coin is 0.5. So instead of doing what we do in linear regression, which is to model the expected value of the outcome directly on that scale, why don't we model the expected value of the outcome, which is the probability? Why don't we model that with something like this? E to the linear regression over 1 plus e to the linear regression. Well, this right here, this equation, if we invert it and if we go back, we work with it a little bit, we get that it says that the log of the odds is the linear regression relationship. So what we're doing in binary generalized linear models is, in this particular logistic regression, we are taking a coin, we're modeling our data as if it was a bunch of coin flips where the success probability changes with I, and we're relating the coin, that success probability, to our regressors by taking the log of the odds of that probability associated with that probability. So you can go backwards. This is the log of the odds. Okay, you could go backwards to the probability using this equation up here. And I like to call, e to the a over 1 plus e to the a, this function that inverts the log of the odds back to the probability. I like to call it the x bit. So the log of the odds is called the logit. I like to call the function that goes backwards the x bit. Okay, so that's all we're doing. That's all we're doing. But that's the clever bit of generalized linear models. We're not actually putting the model on the scale, we're not actually putting the linear regression parameters, defining an inequality between the outcomes and the linear regression parameters. Instead, we're saying that the outcome depends on a probability distribution. That probability distribution depends on the success probability. That success probability then depends on the regressors. Okay? So interpreting logistic regression is pretty straightforward. And I should mention, all the logs that we do in these notes, these are natural log. LOG meaning natural log in this case. Most mathematicians, when they write LOG, they mean natural log. So in this case, what happens? So if I were to plug in a 0 for the Ravens score, I would just get beta 0, B0. So B0 is the log odds of a Ravens win if they score 0 points. Then E to the B0 over 1 plus e to the b0 would be the probability that the Ravens won. The model-based probability that the Ravens win if they score 0 points. Now, in this case, this is maybe a not perfect component of this model because it gets estimated to be non-zero, and we know that the team can't win if they score 0 points. They could tie, but they can't win. So B1, okay, so remember how we interpreted our slope coefficient from before. We have B0 plus B1, and let me put in the Ravens score plus 1, okay, and subtract off B0 plus B1 times the Ravens score by itself, okay, and then let me put brackets around that, okay. Then that equation, if you work it out, that equation works out to be B1, okay. So what is this? This is the logit of the probability that the Ravens win given the score plus 1. And this is the logit of the probability that the Ravens win given the score itself. So what is B1? It's the increase or decrease, depending on whether it's positive or negative, in the log odds of the probability that the Ravens win, associated with a 1 unit increase in the regression variable, or in this case, a 1 point increase in score. Okay? And if we exponentiate this, remember that if this is a difference on the log scale, so if we exponentiate it, we get a ratio back on the original scale. So if we exponentiate this, we get that e to the b1 is then the ratio of the odds comparing a 1 point increase in score. The ratio of the odds of the Ravens winning for a 1 point score increase. Okay? So, and we don't have multiple regressors like we studied a lot in linear regression. We don't have that for this particular example, but the extension is pretty direct. Everything, just like in linear regression, multivariable regression, everything is just interpreted presuming the other regressors are held fixed. So remember, our interpretation in multivariable regression was that the increase associated with a 1 unit change in the regressor holding the other regression variables fixed. That same interpretation carries over in logistic regression. E to the b1, if we had a bunch of other covariates added in this, let's say whether or not it was a home or away game, if we had that one extra covariate added, then e to the b1 would be the odds ratio for a 1 unit increase in score, the odds ratio of a Ravens win for a 1 unit increase in the score, holding whether or not it was an away or a home game fixed. Okay? So the logistic regression coefficients are pretty easily interpretable. The log is a nice function that allows us to sort of invert additive things and turn them into ratios, and people like to talk in terms of ratios. So it's a very nice interpretation. I want to talk a minute about the history of odds. So it goes back to this idea of a fair game. So imagine if you're playing a game where if you flip a coin with success probability P, and if it comes up heads, you win X dollars, and if it comes up tails, the person you're playing against wins Y dollars and you lose Y dollars. Okay? So what should we set X and Y in order for the game to be fair? Okay, where in this case the coin isn't necessarily a fair coin. It's P is not necessarily 0.5. So what is your expected earnings? Well, if you took the inference class, you would know that your expected earnings is how much you would win given the coin came up heads, minus how much you would lose if the coin given the coin came up tails. Okay? And if we want it to be a fair game, we want our expected earnings to be equal to 0. Well, if we solve that, we get y over x equals p over 1 minus p. So in other words, the odds can be said as how much you'd be willing to pay for a p probability of winning $1. So in other words, setting x equal to 1. And then if p is bigger than 0.5, you'll have to pay more than you lose, and p is less than 0.5, you'd have to pay more than you pay less than if you lose than if you win. And so this is why if you go to the horse betting horse track like Pimlico here in Baltimore, they'll give you the odds against a horse winning. So they'll say 10 to 1. Why would they do that? Because if you bet $1, that would mean if the horse won, you got $10. So you can do the calculation very quickly in your head because they're giving you fair game. And some interesting side notes about the horse betting analogy in that the way in which they set the probabilities for horse betting is they do it in a way adaptively as the bets come in. If more people bet on a horse, the probability of it, that their odds that they say that it's going to win goes up. The odds that they say it's going to lose goes down as more people bet on it. And they do it that way not because they think it's an accurate reflection of whether or not the horse will win, but just to balance the actual money coming in and out so that if that horse wins or loses, they know exactly how much they would win or lose. And they can balance it out that way so they're guaranteed to neither win nor lose money. So, but what's interesting about that is over a long period of looking at horses, that aggregate odds that winds up from the betting, that winds up being a fairly accurate representation of the percentage of times the horse wins. Which is interesting. That just says that people are somehow wise as a collective and they create an efficient, fair market for gambling by virtue of betting correctly in aggregate. And also I would say, so you might wonder how the casino or how the track makes money. They make money by taking a little bit a fee for every bet, and that's so they are basically guaranteed to win. So when the phrase "the house wins" is literally true, it means that the house is basically guaranteed to win. They've set up the odds so that whether the horse wins or loses, they're monetarily neutral, and they take a little money off of each bet. That's an interesting fact. And of course, it's more complicated than that because you've got a big, complex organization, thousands of people running. So, of course, it's far more complicated than that. But that's the gist of it. So, if you want a good risk-free position, become a bookie. So next up, I'm going to show us how to visualize fitting logistic regression curves using a computer experiment. So I look forward to seeing you in that lecture.